When you first start working with an evaluation board, like the Stellaris LaunchPad, you first want to do something simple, like making the LED blink. That implies you understand how to use the development tool, how to initialize the LM4F device and its clocks, and how to send data to the input-output pins. Chapter 3 and its lab will wrap all that together. Stellaris Ware is a license-free and royalty-free source code and library for TI Cortex-M devices. It offers and includes the peripheral driver library, the graphics library, USB library, Ethernet stacks, and in-system programming. To look a little closer at the Stellaris Ware features, the peripheral driver library is a high-level API interface to the complete peripheral set. It's license and royalty-free for use with TI's Cortex-M parts. It's available as object library and as source code. And as source code, it can also act as some pretty nice examples for you to write your own code from. This is programmed in the on-chip ROM of all LM4F devices. Stellaris Ware also includes the graphics library. That's graphics primitives for drawing shapes, text, images on the screen, and widgets to tie touchscreen buttons to in-program actions. We have 153 fonts plus Asian and Cyrillic, and a series of graphics utility tools for converting files and making buttons, and some very interesting stuff that we'll go over later on. We have USB stacks and examples. The device and its stack are USB device and embedded host compliant. We have device, host, on-the-go, and Windows side examples available. TI also has a free vid-pid sharing program that I'll talk about later that can save you as much as $2,000. The Ethernet, we have lightweight IP and micro IP open source stacks with the 1588 precision time protocol modifications made to it, and extensive examples in that. Some other extras. We have the Simplicity wireless protocol available, IQ math examples, bootloaders, like I mentioned earlier, additional Windows side examples for you. There are two in-system programming options for you provided through Stellaris Ware. The Stellaris Serial Flash Loader is a small piece of code that allows programming of the flash without the need for a debugger interface, without using Code Composer Studio. All Stellaris microcontrollers ship with this code preloaded in the flash. It uses the UART or SSI option. This is meant to be a production level, low-cost way of programming the part. The LM Flash programmer interfaces with the serial flash loader, and the application node is there in SPMA 029. The main idea with this is that when the new code is programmed into your flash, this piece of code that's sitting in flash will be wiped out. That's the way that you want it to happen. If you want to restore it, you can go into the programming examples in Stellaris Ware and restore it if you need to. The Stellaris bootloader is preloaded in ROM, or it can be programmed at the beginning of flash to act as an application loader if you like. You can also use it as an update mechanism for an application running on a Stellaris microcontroller, a thing that's called paging. You can interface to this via UART, which is the default, through I2C, through SSI. On those parts that have Ethernet, you can attach to it through that. For USB, we can also do device firmware update as host and device on those devices that have host. The LM4F 120 only has device. This is included in the Stellaris peripheral driver library with full applications examples. There are 4 fundamental clock sources on the Stellaris devices. Well, what do you want from a clock on your part? You would like them to be cheap. You would like them to be accurate. You'd like them to be easy. You don't get to pick all of those for every one of the oscillators on any part. So what we offer you is a precision internal oscillator, which is a 16 megahertz oscillator plus or minus 3%. You do not have to include any crystal or clock source on the outside of the device. We have a main oscillator that uses an external single-ended clock source, or it can use an external crystal. We have an internal 30 kilohertz oscillator. This is a 30 kilohertz plus and minus 50% oscillator. This is intended for use during deep sleep, power savings modes, when you really don't care exactly how fast the processor is running. All you want to do is kick it over and maybe poll for some activity. We also have the hibernation module clock source, which runs off the 32768 Hz crystal. That's intended to provide the system with a real-time clock source. The system clock, or the CPU clock, can be driven by any of the fundamental clocks: the internal 16 MHz, the main oscillator, the internal 30 kHz oscillator, and the external real-time oscillator. Plus, we have an internal phase lock loop that runs at 400 MHz. No, you can't run the CPU at 400 MHz. The dividers on there limit you to 80 MHz and below. We also have the internal 16 MHz oscillator divided by 4, so that would be 4 MHz plus and minus 3%. So you have 1, 2, 3, 4, 5, 6 different clock sources that can drive the CPU. The internal 16 MHz that can also drive the PLL. The internal 16 MHz divided by 4, the main oscillator, 16 MHz, the internal 30 kHz, the hibernation module, and the phase lock loop. So let's take a look at the clock tree to fully understand that. This is the Stellaris clock tree. It's a very flexible implementation to provide you with all the different types of clocks that you'll need for low power operation, for low cost operation, for high precision operation. Let's take a look at the system clock on the far right in the middle, where it says system clock. If we follow that back to the mux, that allows us to either divide by the sysdiv or to bypass it. We also have a divider before that, and then you'll see the div 400 that's divide by 2, or it bypasses there. Then you'll see the PLL, the 400 MHz PLL. That can be driven by the main oscillator. That can be driven by the precision oscillator. Either one of those. So let's say that we take a 16 MHz crystal. There's a limitation on the part for what crystals you could use to drive the PLL. We use the main oscillator to drive the PLL. The PLL will run at 400 MHz. There's a divide by 2 that divides it to 200 MHz there for that very center mux. Our sysdiv then will divide it further. Normally you might divide it by, let's say, 5. 5 would give you 80 MHz for your system clock. So how are you going to program all of those? There is a single driver-lib API function call called syscontrol_clock_set. That sets the sysdiv divider setting for you. It tells you whether you're running off the oscillator directly or if you're running off the PLL, whether you're running off the main or the internal oscillator, and what the crystal frequency is on the outside of the device. So it's very easy to set up your system clock with this single API. Stellaris General Purpose I/O is extremely capable. Any GPIO can be an interrupt, either edge triggered on rising, falling, or both. It can be level sensitive on high or low values. Any GPIO can directly initiate an ADC sample sequence or a DMA transfer. The toggle rate can be as high as the CPU clock speed on the advanced high performance bus. Now, most of the ports on the LM4F120 H5QR can be configured to be on either one of the buses, the advanced high performance bus or the advanced performance bus. If you're on the standard bus, the advanced performance bus, you get half the CPU clock speed. That's what you generally expect, where you toggle a GPIO. But you can achieve a higher rate at a slightly higher power cost on the advanced high performance bus. In input configuration, all of the GPIO are 5 volt tolerant. You can program the drive strengths to be 2, 4, 8 milliamps. The slew rate, you have slew rate control for the 8 milliamp setting. You can imagine what would happen if you have 20 different GPIO all going to 8 milliamps simultaneously. You really need a slew rate control on that. The pins have programmable weak pull up, pull down, and open drain modes, and the pin states can be retained during hibernation mode. So we can come right back up from hibernation, which is essentially from power up, and remember what the pin states were of the device and set them. GPIO address masking is a somewhat unusual application of the bit banding technique. Each GPIO port has a base address. And if you look in the diagram there, GPIO port D, that base address for that peripheral is at 4005.8000. So that's the base address for that port. You can write an 8-bit value to the port directly to that base address, and all 8 pins will be modified, just like you've done the port addresses since the beginning of the 6502 days, if you're that old. If you want to modify specific bits in an older processor, you would have to read the value in the port, change the value that you want to, and write the values back out to the port, preserving the old ones. Here, you can use a bit mask to indicate which ones of the bits that you want to be modified. So this is done in hardware by mapping each GPIO port address to 256 separate addresses. So it's an addressing trick. Bits 9 to 2 of the address bus are going to be used as a bit mask. So in this case, the register that we want to change is GPIO port D. There's its address. The current contents of the register, and you can see it's 00011101. The value that we're going to write to it is EB. Now, if we had done this, if we had wanted to preserve some of the values in the bits in an older style processor, and we just wrote this value to the port would now have EB. But that's not exactly what we want to do. Instead of writing to the GPIO port directly, what we're going to do is we're going to use a bit mask, and we're going to specify that bit mask as shown. And you can see in the bit mask that the 9 to 2 in the bit mask, the bottom one is a 0, and then the next one is a 1, and then a 1, a 0, a 0, and a 1. Only the bits with 1s in them will be changed in the final port. So only the bits marked as 1s in the bit mask get changed. So you can see right here that we have the 1 from EB matching up with the 1 in the bit mask, writing a 1. The 0 in the EB matching up with the 1 in the bit mask and writing a 0. So, and lastly, the 1 and the 1 matching a 1. So now the new value in GPIO port D, notice that only the red bits were written. So we did a read, modify, write as an atomic operation without having to read anything back from the port. Down below is a specific example of that. Here we're going to do a GPIO pin write to GPIO port D base. That's the port D base that we specified up here. We're going to write to GPIO pin 5, to pin 2, and the pin 1. So we will only write those values out of the data that we actually send to it. This is an extremely powerful technique, and you're going to get to see that in detail in the lab. Lab 3 is your first chance to write some real code from a blank page. If you don't understand what a Stellaris Ware API function call does, or what a parameter means, pause the video and look it up in the user guides that you found in the first chapter of the workshop. We've provided plenty of explanation in the lab steps, but make sure you take the time to comprehend what's going on, rather than skipping on to the solution. Your hard work will be rewarded. In Lab 3, Step 1, maximize CodeComposer Studio. On the CCS menu bar, select File, New, CCS Project. Make the selections shown below. Again, make sure you uncheck the Use Default Location checkbox and select the correct path to the CCS folder you created. To reiterate, this step is important to make your project portable and in order for the include paths that we're going to be entering into the project properties to work correctly. In the variant box, just type 120 to narrow the results in the right-hand box. In the project templates and examples window, make sure you select Empty Project with main.c. and click Finish. When the wizard completes, if the Grace tab or the TI Resource Explorer appears, close them, and then click the plus next to Lab 3 in the Project Explorer pane to expand the project. Note that CCS has automatically added main.c to your file in your project, like we asked from the template. Now, we placed startup under ccs.c in the folder beforehand, so it was automatically added to the project. Again, that startup ccs.c is available in any of the Stellaris Ware examples. We also placed a file called main.txt in the folder, which contains the final code for the lab. If you run into trouble, you can always refer to that file. In step 2, delete the current contents of main.c. Now, I would suggest that you copy-paste from the PDF file to prevent having typo errors. If you want to type this, you can certainly type it. We're going to be copy and pasting from the PDF file off screen on a second monitor. So take the lines that you see, the 5 lines of code, and paste them into your main.c. The top line, the hardware memrap, those are the macros that define the memory map of the Stellaris device. The HW types define some common types and macros like Boolean and the registers. The syscontrol defines the macros for the system control API in DriverLib. The GPIO.h defines the macros for GPIO, the API for DriverLib, and some functions like the GPIO pin type and stuff that we'll be using in a second here. The int pin data equals 2 creates an integer variable called pin data and initializes it to 2. We're going to use that to cycle through the 3 LEDs, lighting them one at a time. You'll also notice, if you didn't already in Lab 2, that there are question marks to the left of every one of those. This tells you immediately that Code Composer says it can't find those. We're going to fix that in just a moment. In step 3, we're going to drop in a template for our main function. Leave a line for spacing and add this code after previous declarations. If you type this in, notice that the editor will automatically add the closing brace for you when you add the opening one. Why wasn't this thought of earlier? In Lab Step 4, we're going to deal with the clock setup. We're going to configure the system clock to run using a 16 megahertz crystal on the main oscillator. That's what's on the board, driving the 400 megahertz phase lock loop. The 400 megahertz PLL oscillates at only that frequency, but it can be driven by crystals or oscillators running between 5 and 25 megahertz. There is a default divide by 2 divider in the clock path, and then we're specifying another divide by 5, which totals 10. That means that the system clock is going to be 40 megahertz. So enter this single line of code inside main. This is the sys control clock set. You can see it says divide by 5, use the PLL, use the crystal at 16 megahertz, and make sure you use the main oscillator. The next drawing is an excerpt from the LaunchPad board schematic. Note that the crystal attached to the main oscillator inputs is 16 megahertz, while the crystal attached to the real-time clocks is 32,768 hertz. In Lab Step 5, before calling any peripheral-specific DriverLib function, we have to enable the clock for that peripheral. If you fail to do this, it will result in a fault ISR, an address fault. It's a common mistake for new Stellaris users, and I've made it myself. The second statement below configures the 3 GPIO pins connected to the LEDs as outputs. The excerpt below of the LaunchPad board schematic lets you see that port F pin 1 is connected to the red LED. Port F pin 2 is connected to the blue LED, and port F pin 3 is connected to the green LED. So leave a line for spacing and enter these 2 lines of code inside main after the line in the previous step. That is to turn on the peripheral, the GPIO F, that's port F. We're going to turn on that peripheral, and then we're going to set those pins as outputs. The base address of the GPIO ports listed in the user's guide are shown below in the workbook. Note they're all within the memory maps peripheral section shown in Module 1. APB here refers to the advanced peripheral bus, while AHB refers to the advanced high performance bus. The AHB offers really good back-to-back performance, much higher than the APB bus. GPIO ports that are accessed through the high performance bus can toggle every clock cycle versus once every 2 cycles for ports on the APB. In power-sensitive applications, the APB would be a better choice. In our labs, GPIO under port F under base is 0x40025000. That means it points to the APB bus. In lab stack 6, finally create a while 1 loop to send a 1 and 0 to the selected GPIO pin with an equal delay between the 2. If you look in the code at the bottom down here, there's the while loop that we're going to drop in. The sys control delay is a loop timer provided in Stellaris Ware. The count parameter is the loop count, not the actual delay in clock cycles. To write to the GPIO pin, use the GPIO API function call GPIO pin write. Make sure to read and understand how the GPIO pin write function is used in the datasheet. The third data argument is not simply a 1 or 0, but represents the entire 8-bit data port. The second argument is a bit-packed mask of the data being written. In our example below, we're writing the value in the pin data variable to all 3 GPIO pins that are connected to the LEDs. Only those 3 pins will be written to based on the bit mask specified. The final instruction cycles through these LEDs. The final instruction cycles through the LEDs by making pin data equal to 248, 248, and so on. Note that the values sent to the pins match their positions. A 1 in the bit 2 position can only reach pin 2 on the port. Now might be a good time to look at the datasheet for your Stellaris device. Check out the GPIO chapter to understand the unique way the GPIO data register is designed and the advantages of this approach. Leave a line for spacing and then add this code after the previous step. If you find that your indentation doesn't look quite right, hit Control A, right-click on the selected code, select Source, and then correct indentation. There's also a lot of other great stuff under the Source and Surround With selections. In step 7, click the Save button to save your work. Your code should look something like what you see below in the workbook. I'm sorry about the small font, but any larger font made the syscontrol clock set instruction look pretty strange. If you're having problems, you can cut-paste this code into main.c, or you can cut-paste from the main.txt file in your lab3/CCS folder. If you were trying to build this code right now, please don't. It would fail. Note the question marks next to the include statements. Code Composer has no idea at this point where those are located. We still need to add the startup code and set our build options. In Lab Step 8, in addition to the main file you've entered, you'll also need a startup file specific to the tool chain that you're using. This file contains the vector table, startup routines, clear the BSS section, default ISRs. We've included this file in your folder. Double-click on Startup under CCS.c in your Project Explorer pane and take a look around. Don't make any changes at this time. When you're done looking around, you can close the Startup CCS.c editor window. In Lab Step 9, right-click on Lab 3 in the Project Explorer pane and select Properties. Click Include Options. Here we go. Click Include Options under the ARM compiler. In the bottom Include Search Path pane, click the Add button and add the following search path. You can see what that says. It's project root, and then it's // and so on. If you followed the instructions when you created your Lab 3 project, this path 4 levels above the project folder will give your project access to the include, the INC, and the driver lib folders. Otherwise, you'll have to adjust the path. You can check it for yourself using Windows Explorer. I would suggest copy and pasting from the workbook PDF for this one and the next steps. When you're done, click OK. After a moment, you'll notice that CodeComposer will refresh the project, and you should see the question marks disappear from the include lines in main.c. We're not quite done yet. Right-click on Lab 3 again in the Project Explorer pane and select Properties. Under ARM Linker, click File Search Path. We need to provide the project with the path to the M4F libraries. Add the following include library file as shown in the workbook to the top window. This is a path to the driver lib-cm4f lib. Of course, again, if you did not follow the directions when you created the Lab 3 project, this path will have to be adjusted just like the previous one. When you've done that, click OK to save your changes. In Lab Step 11, compile and download your application by clicking the Debug button, the one that looks like a bug, on the menu bar. If you're prompted to save changes, do so. If you have any issues, correct them, and then click the Debug button again. There's a variety of hints. There's a hints page in Section 2. After a successful build, the CCS debug perspective will appear. Click the Resume button to run the program that was downloaded to the flash memory of your device. You should see the LEDs flashing on your board. If you want to edit the code to change the delay timing or which LEDs are flashing, feel free to go ahead and do that. Instead, we're going to move ahead. Pause the code execution by hitting the Suspend button on the debugging toolbar. If you get the message, no source available, close the Editor tab. Again, that source code for that function, we're using it as a lib file. It's not present in our project. In Step 12, click on the following line of code in main.c at the top of the while loop. It's the GPIO pin write instruction that writes pin data. Right-click on that line of code and choose Run to Line. This will run your code until it hits this line of code. Think of that as a temporary breakpoint on that line. Note the blue arrow on the left indicating where the program counter is now pointed. In this case, we've already double-clicked on the variable pin data and right-clicked on it and set Add Watch Expression so we can see it in the watch window here. Click the Step Over button a few times to single step through the while loop. Notice how the value of pin data changes as we reach the bottom of the loop. If you're also watching the board, you'll see the colors change as you hit the top of the loop. The top GPIO pin write will write the different color to the board. Okay, depending on where you've reached there, as in steps 12 and 13, run to that top line of code, GPIO pin write, by right-clicking on it or just step there. Before we execute this top line, though, in step 17, let's change the value of pin data in the expressions pane. Click on the value of pin data up there, and notice we can now edit the value. Change the value to 0x0e. That's 14. That's 8 and 4 and 2. In other words, let's turn all 3 LEDs on at the same time. So with it set to 14, click the single step line once. So what do you see there? Well, I see a mostly white color, meaning that all 3 LEDs are on at the same time. In step 19, single step through the while loop. Notice how all the LEDs go off as expected and how pin data gets set now to 1C or 28 at the end of the loop, because all the loop is doing is multiplying by 2. The original loop control depended on pin data only having values 2, 4, and 8. Setting pin data to a different value might be a problem. So now we're going to explore the Stellaris pin masking feature. In step 20, again, as in steps 12 and 13, run to the line that includes GPIO pin write function at the top of the code. In step 21, remember, because of the bit mask we're using in the GPIO pin write call, only bits 2, 4, and 8 in pin data control the LEDs. Pin data is currently 1 Charlie or 28. Right-click on the value of pin data in the expressions pane and select Number Format Binary. You might have to resize the expressions pane so you can see all the bits as shown in the workbook. Remember from the schematic that bit 1 is red, bit 2 is blue, bit 3 is green. Bit 0, the bottom one, is not connected to anything. With that true, only the blue and green LEDs should light. The 1 in bit 4 is not relevant and won't be written to the port because of the bit mask. In step 22, click the Step Over button to run the GPIO pin write function. So what color do you see now? In our case, it looks like a blue-green color, which makes sense because the blue and green LEDs are lit. In step 23, again, as in steps 12 and 13, run to the line that includes GPIO pin write function at the top. When you reach that point, your expression should now look like what's shown. At the bottom of the pin data, it should be 111000. With only one bit out of bits 1, 2, and 3 set, what color do you expect to see? Click the Step Over button to run that first GPIO pin write. So did you expect to see a green? All we see is the green LED, which is the only one that's lit, which is the only one that the pin mask will allow to light. In step 24, click on the value of pin data in the expressions pane and change the value back to 2. Click on the Run button or the Resume button to run the code. And the code looks like it's working pretty well. In step 25, when you're convinced everything's running correctly, click the Terminate button to end your debugging session and return to the CCS Edit perspective. Right-click on Lab 3 when that's done in the Project Explorer pane and select Close Project to close the project. In step 27, hey, how about a homework idea? Look at the use of the Buttons Poll API that's in the quickstart rgb.c file in the quickstart application folder. Write some code to use that API function to turn the LEDs on and off using the push buttons.